Today, we are diving deep into one of the biggest questions in all of science. What if the fundamental rules of our universe aren't random at all? We're going to look at a really fascinating paper that suggests a single, elegant key could unlock the secrets behind reality itself. You know, our whole understanding of the cosmos is really built on just a handful of numbers. We call them the fundamental constants, and they dictate absolutely everything from how fast light travels to how strong gravity is. But here's the mystery that's bugged physicists for decades. Why do they have these specific values they do? Are they just some random cosmic lottery numbers? I mean, just look at the speed of light, c. It's the ultimate speed limit in the universe. It's not some nice round number. It's just, well, this very specific value. Or how about the gravitational constant, g? This tiny, tiny number governs the pull of every single planet, star, and galaxy. And again, it's this super precise and, frankly, kind of weird value. And then you've got this guy, the reduced Planck constant. H-bar, we call it H-bar. It's the fundamental unit of action in the completely bizarre world of quantum mechanics. Here's the kicker. If you change any of these numbers, even by a tiny fraction, the universe as we know it would just poof, it wouldn't exist. So for a long time, we've basically just treated these numbers as brute facts. We measure them, we plug them into our equations, and that's that. But what if that's completely wrong? A recent paper by Sung-Hin Hong puts forward a really radical idea that these constants aren't random at all. Nope. Instead, they are all the inevitable results of one single, incredibly simple geometric rule. All right, so the paper calls this big idea the minimal phase mismatch. This is supposedly the one foundational geometric rule that acts as the generator for everything else. Okay, so what on earth does that mean? Well, try to imagine a tiny, unavoidable wobble, or maybe think of it like a geometric glitch that's baked into the very fabric of reality. The paper argues that if you take the simplest possible closed system you can think of, just a loop of 3 nodes, there's a fundamental frustration that you just can't get rid of. It's not a physical thing, it's a purely mathematical property of the structure itself. And here's the amazing part. This unavoidable little glitch has a precise value. It's pi divided by 3. Now, according to the paper, this number isn't something you measure in an experiment. It's not a guess. It is structurally forced into existence by nothing more than pure geometry. So how does this actually work? Well, imagine 3 points, like the corners of a triangle. And the only rule is that each point has to force its neighbor into an opposite state. So point 1 makes point 2 its opposite. Point 2 then makes point 3 its opposite. But you see the problem? When point 3 tries to make point 1 its opposite, you hit a snag. An odd number of flips just doesn't get you back to where you started. That leftover tension, that geometric frustration, when you spread it out over the 3 connections, is exactly pi over 3. Okay, so we have this one fundamental number, pi over 3. Born from pure geometry. Yeah, for the really wild part. Let's see how the theory claims this one number can build the most important rules of our entire universe. The paper claims that by taking this pi over 3 generator and applying it to different geometric layers, or what it calls shells, you can actually derive the core values for c, g, and h. And here's the absolutely incredible part. When you take these theoretically derived numbers and convert them into our physical units, they don't just get close. They are a perfect match to the values we've measured for decades. So this quote from the author is the crucial point. 0 internal residual. What that means is no fudge factors, no little numbers you have to tweak to make the math work, no leftover bits that need explaining away. The theory, it claims, just spits out the correct values for the speed of light, gravity, and the Planck constant from this one geometric idea, perfectly. But wait, the story doesn't end there. It can't be that simple, right? Well, not every constant fits this perfect picture. And honestly, this is where the theory gets even more interesting. Let's take a look at something called the fine structure constant. So the fine structure constant, which we call alpha, basically governs the strength of electromagnetism. The paper's geometric rules give us a baseline prediction for what it should be. But when you compare that prediction to the unbelievably precise value we've measured in countless experiments, you find a little problem. They don't quite match up. The theoretical prediction is off by this tiny, but scientifically massive, margin of about negative 0.003%. Now, for a theory that's claiming perfect closure, is this where the whole thing just falls apart? Well, in what might just be the paper's most fascinating claim, it argues that this little mismatch isn't a failure at all. Instead, it says it's a predictable, discrete bit of geometric residue, something it calls a quantized leakage unit. So the theory doesn't just stumble upon this error, it actually predicts its exact value. The paper argues that this deviation is precisely equal to our original generator, pi over 3, but subdivided by 12. So it's not random noise, it's just another layer of the geometric puzzle, a predictable leakage that shows up when you build a more complex structure. Okay, let's just step back for a second and really think about the massive implications here. If this whole framework actually holds up, it suggests that the fundamental laws of our universe aren't some random dice roll. Instead, they might be the inevitable, unavoidable outcome of a single, self-contained geometric principle. So let's just recap the core claims here. You have one single geometric invariant, pi over 3, and it generates everything. The speed of light, gravity, and Planck's constant pop out of it perfectly. The fine structure constant is almost perfect, with a tiny, predictable deviation that is also part of the geometric structure. And the craziest part? All of this is supposedly done with zero fitting parameters. Now, of course, this is all highly theoretical. But here is the critical part for any new scientific idea. The paper actually makes a falsifiable prediction. It calculates a specific and, yes, an incredibly high energy scale where the effects of this underlying geometry should start to become obvious. We can't reach that kind of energy with our tech today, but it gives us a concrete target. It's a way the theory could, someday, actually be proven wrong. And that leaves us with a really profound final thought. If the most fundamental numbers that define our entire reality all just stem from a single, simple geometric frustration, what else is hiding in that geometry? What other secrets of the universe are just sitting there, waiting to be derived instead of discovered?